Hi, welcome to this Open Security Summit session in June 2021. I'm actually going to do two sessions in one, kind of probably the part one of it, and now we'll continue next month on evolution of this. So I'm going to talk first about the idea of scaling Kubernetes, one pod per file, and how we've done about it and how we've been doing it at the company I work for at the moment. And then I want to follow up with the idea of how you actually test it, right? And some thoughts about it on actually how you evolve that thinking. So the first thing is, what we go to the point where we're using Kubernetes as an operating system, right? So for me, the biggest advantage of Kubernetes is that it provides a common framework to execute tasks, right? And of course, there's tons of plumbing around it, tons of architecture and capability that it has. But fundamentally, what I really like is this ability to schedule and execute basically pods and containers, right? And of course, container is just a pod is just a collection of containers, right? But it's quite interesting to think of Kubernetes as the operating system, right? Which is basically means that if you design for Kubernetes, you are already sort of cloud native, right? Where if you design for a particular cloud, you very quickly become basically, locked into that cloud. So it's almost the difference is, what is your OS? Is it VMware? Is it AWS? Is it Azure, Google Cloud, IBM, Oracle, those clouds that exist, or is it Kubernetes? And the logic that we followed was to say, we want to build a solution that is Kubernetes native first, and then when we are at a particular platform, we leverage some of the cloud platform things. Because there's some things you can still do in Kubernetes, but it's better to then be specific to the cloud. Some of the autoscaling, some of the load balancing, some of the secret management, those are better when you have two solutions, one Kubernetes native, one cloud native. And one of the the interesting thing is that every time we talk about Kubernetes, there's lots of people that have tons of horror stories, right? It's quite interesting that everybody that when I remember in this journey, people going, they were like, are you sure you need Kubernetes? Are you sure that that's the right way to do it, right? Because when there's some really cool website here where it actually talks a lot about the Kubernetes horror stories, and it's interesting to look at them, right? It's interesting to understand the reason why, how you shoot yourself in the foot, the kind of things that you can do well with Kubernetes. And when I look at it, right, I still feel that a lot of it comes down to this idea of clusters collapsing or clusters having side effects. Treat some of the instances okay, managing your nodes, right? Make sure that when you have basically this thing here where you create a cluster, you run your tests, and then you delete the cluster, or you upgrade things, right? And like I say, you upgrade cluster, etc. And this is sort of comes down to that idea of almost pets versus cattle, right? There's this really interesting idea in technology where it kind of comes from this. I think it comes from this presentation that this guy did, in 2016, where this idea that, in the old way of doing things, we treat our servers like pets. I remember this, I remember the servers with specific names or, or stars or Star Wars references or whatever, right? So you got these servers, right? And then basically you have to make sure you maintain it. You have to make sure that, if that server, has anything is done manually, it's not easy to replace. And this is, not just automation, right? It's the fact that there's lots of knowledge, there's lots of things that goes into maintaining a system that if you cannot automate that, if you don't capture that in a repeatable state, even you sometimes can do it, next time. But more importantly, if that person leaves or that person moves on, you don't start to understand how these things work, right? And I actually feel that one of the things we should be monitoring and measuring more is how many systems exist that the company is not really able to move the data around, is not able to move the applications around from that system. So the idea here is that, you want to treat your solution not as a pet, but kind of as cattle, right? As like a herd where, like you got these servers and they're disposable, etc. The way I now think about this is that I think a lot of times we kind of stop, for example, at Kubernetes, we stop at the cluster level or we stop at the node level. And you find that your clusters are still like pets, right? You still have to maintain it. It's interesting that you see a lot of effort on how to upgrade a cluster, how to maintain it, how to upgrade nodes, how to do all sort of stuff, because the cluster becomes your pet, right? You have 2 clusters, 3 clusters, 10 clusters, right? Or maybe 1 in some cases, right? Or you have some in like kind of load balancing, red, blue, kind of for disaster recovery, but it's fundamentally mainly 1 cluster, right? And it kind of sometimes doesn't help when you use managed service providers, because although they provide a lot of good things for you, they also sometimes abstract you for some of those things, right? And then that can cause some problems. So, I actually found that this really cool article, right, which is basically how to treat a Kubernetes cluster as cattle, right? And what these guys do here is basically they in this company, right, they basically they develop. Of course, you need to develop lots of tools to do this, and some of them they publish, like I think Cube One or something else was published by them. But the idea is that they publish and they deploy Kubernetes clusters as you actually would, open source Kubeon, right? As as part of your flow. So instead of having 1, 2, 5 clusters, you have 20, 30, and also you deploy them for dev, QA, CI pipeline. But we actually take it to the next level where we actually do it again. We deploy that in production. So I think that's super important. So I'm going to talk quickly about the Glassware CDR platform. And by the way, this bit is open source. The only part that's not open source is this binary here. And basically, this is kind of how we set up, right? We basically set up that, we got this binary, which basically is our the ability to create safe files. And I go into a bit of a detail in that because that's important. We package that inside Docker, and then we run it on Kubernetes, right? And the idea is that the binary does the transformation. This is a file-based transformation, so file from unsafe files to safe files, but this could be from A to B, DLP, sandboxing, processing, even data science, right? Basically, it does something to a file. There's a clear input and an output. We put that inside a Docker, right? So we make it easy to consume the binary. We package everything up, and then we orchestrate the Docker in Kubernetes, right? So we can run thousands, even millions of pods. And the key thing here, which I'll cover more, is we run the Docker as basically Docker pod is 1 pod per file. So that was the other thing that sometimes we found in Kubernetes is there's actually quite long-lived executions, which I kind of don't like, right? I like the idea things recycle very quickly. There should be very little state. You almost want this environment where things start when they're not needed to get destroyed and then they go up and down, right? So this is become a very powerful workflow where what we actually have is this environment where each of these gets destroyed every time. And the power of this, and this is where you have to think about, like when you do this, there's lots of advantage, but then you get to the point of how you test it, right? How do you test an environment that all of this gets created and destroyed as part of the day, right? So all of these bits here is now ephemeral. And that's the thing that's interesting, right? The thing that's interesting here is that the way that our approach, in this case to Kubernetes, is that both the pods and the Kubernetes are ephemeral, i.e. they only last for a little bit. They could be there, they could be not there after a while. We actually scale up by creating multiple Kubernetes clusters instead of actually starting multiple nodes, which is a different model, right? So very quickly, what Glassware does, and basically instead of looking for non-bad AV and this for non-bad like detonation chambers, the CDR, which is we are part of an industry that does this. There's lots of players out there. It's kind of called content design and reconstruction, which is created by Gartner. And fundamentally, you inspect the file, you clean the file, then you rebuild it, and you deliver the file. Now, the thing that is very important, relevant for this, is the fact that we are processing malicious files. So basically, it's like imagine like we are looking at files that are potentially malicious, and one of the things that we want to make sure is that we have a pristine environment every time, which is raises also lots of questions from a testing point of view. Actually, ironically, makes testing easy because by design we actually are going to create an environment that we can create the test environment very quickly and very easy to replicate. So, very, very kind of, that's just a top level view that the websites need to decide, fundamentally, instead of flattening a file, we actually give the save file to the user, right? So the question is, when we process the file here, right, how do we do it in a safe way, right? And this is just shows that, you get a safe file from day 0 versus if you go that way, if file is kind of malicious, right? So here's the platform, right? This is where it gets interesting, right? So what you have here is our open source platform, right? Because this pod is the one that contains the proprietary bit, right? So all of this is open source. And what you have is basically the workflow here is for ICAP, but we have the same thing for APIs, where we intercept a file using a proxy. The file goes to a load balancer and it hits the first pod, which is the ICAP server. And the ICAP service in this case puts the file in the store, puts a message in the queue, and then that gets picked up by this message queue, with this service here who starts a pod. So this is the beginning of that one pod per file. So, and then once the pod finishes, puts the result in the adaptation outcome, puts the message in the rebuild store, and then continues. So this pattern is really powerful, right? It's a really cool platform, because what it does, it really allows the system to scale quite nicely, because all the ICAP service needs to do is take a file, put on a store, right? So this part here scales really nicely, right? Because the ICAP, and then the API, you see that it's actually all it's doing is taking a file and putting on this particular message queue and the store. Is the adaptation service that monitors that queue and then starts a pod, right? And this pod, instead of having a long running sets of pods, we only have one pod per file, right? And that means that with the pod, when it's finished, gets destroyed, and then what you have is a new pod coming along, right? And I'll talk about some of the challenges that we had with it, some of the scalability, but also some of the testing challenges that we had with this, right? Which is kind of the things I want to cover here, right? So the way we scale this is that we don't scale by adding lots of nodes, right? So you know that the normal thing of Kubernetes, you got the cluster that has nodes, multiple nodes, and then has the pods inside of it. And one of the things that when we're doing a lot of research on scaling to hundreds of thousands or even millions of nodes, there's a moment where you fight in Kubernetes, right? There's a moment where you're running out of IPs, you're running out of ports. Kubernetes doesn't scale, you're running out of bandwidth, right? Then you have problems of understanding, exactly which node holding what and distributing it. It actually got complex very fast. And one of the things that we realized with architecture is because it's file in, file out, we don't have a huge requirement of state in between. So what we actually done was we actually scale by creating lots of clusters. So even in this case here, what you actually have is, for example, 6 clusters on 3 different regions, which could even be, and then in fact, we even do this on availability zones. And then what you have is we start more clusters as we need and as the traffic increases. And of course, now the key is that you need to test this, right? One of the things I sometimes see a lot is that you need to start treating your auto-scaling testing as almost a whole set of scenarios, because you need to be able to, scale up, make sure the traffic is up, and then go down and do all sorts of testing. And in our case, we basically scale by creating more clusters, which is super powerful. So in this case, just a variation of the same design, but you have a REST API. So you can see that instead of having the ICAP service, you have a REST API, and then we actually have a service that we actually have another product that we created that is called folder to folder, and actually that sends a huge amount of traffic to this. So that's designed to process, gigabytes and terabytes of files sending here, right? The key element, right, of this is to understand that this pod, which actually at the moment we're using the Glassware pod, but this could be any other service, any other transformation that you want to do. Another good example is extract metadata from file, convert files from one format to the other, do file compression, etc. Any kind of task that you want to do, even machine learning analysis, right? You only do it once and then you destroy the pod. And that has actually a lot of advantages, because we actually know that the new pod is exactly the same as the other thousands or hundreds of thousands that we executed before. So it's really cool because you don't have state, you don't have anything that continues from one to the other, and it's literally create a pod, create a container, do a bunch of stuff, then destroy the pod. And I'll walk you a bit more through how we do it. And then there's a couple of workflows that you've got. We actually have an event submission service. So again, the key of this is these queues, which again, from a scalability point of view, but also from a testing point of view, they become very relevant, because the system is all designed to scale based on queues. So you put the stuff in the queue and that gets picked up as the resources are available. And the same thing here, when we want to submit events, we didn't want the event submission to be a bottleneck. So we send first all the events from the thing into a queue, then that gets picked up by a service that all he has to do is monitoring that queue and save it to disk, right? Or in this case, or persist it, right? And then, we got a policy update, etc. And then we actually use Prometheus, right, to monitor and to capture all the data. And in fact, we start to now create endpoints where we use Prometheus already from QL, I think, or from whatever they call it, the data, which is a really great way to expose information, right? And that's actually something that we started to add recently that works quite well. So this is the key, right? So we actually, the original design, we actually, looked at, instead of having clusters with multiple nodes, which actually introduces some interesting challenges, right? Because you still have to auto-scale your clusters. You still have to auto-scale your nodes. So the thing that I found interesting was that, when I was talking to people, says, well, but if you don't do auto-scaling of nodes, then what's the point of Kubernetes, right? And my answer was, look, Kubernetes already gives a huge amount of value, right? Without the node scaling, right? Node scaling is just a nice thing that it does, but actually introduces lots of problems, right? From the fact that in some environments, all the nodes have to be the same in terms of machine sizes, to, for me, the bigger one is that you still need something to start a node, right? You still need to have an entity that understands, oh, I'm running out of traffic, I'm running out of my environment, I'm running out of memory, I'm running out of CPU, I need to start a node. And that's where the complexity becomes, because you either have a Kubernetes cluster that understands where he lives, so he needs to know, oh, I'm on AWS, I'm going to now start stuff directly, or you have an AWS environment that scales for you, and then you have to register the nodes with the cluster, right? And that's why then you have solutions like Rancher and others that do a bunch of other stuff, and Azure and AWS have some really cool things. But I found that, it's almost like you have a level of complexity you might actually not need, because if your cluster is self-contained and you have everything you need inside the cluster, then you might as well, instead of starting a node, start a cluster, right? And then the only question is, what is the overhead of your cluster, right? Or to actually, in addition to what you need to process. And in fact, what we found in our case, we don't have a massive overhead because, most of our supporting services are that, because the real action happens inside, in this case, the Glassware container, which is does the work. That's where you need the big service. That's where you scale. So this worked really well. And then we have one pod per file. So what we then have, actually now we processed, and one container per pod, although we played around a little bit with side containers for some data extraction. So you actually have this mode where you just need compute, right? You give compute, right? The compute has a cluster, the cluster has all the node, has everything it needs, and then you actually don't have to worry about, a lot of other things, because, if you need more compute, more processing power, you start more nodes, and you just put a load balance in front of it, and off you go. And actually, I'm getting to the point where I really like to even break our even clusters into smaller clusters where you do the same thing. You start to have very, for example, like one interesting design here is that why, if you look at this, right at the moment, we have a Kubernetes cluster here, right? But actually, we can look and say, actually, there's a very clear separation of duties here. So this guy here could actually be a cluster, right? Just a full cluster. And then I could actually have just that part, just the C# API, just the REST API, just everything you need to be an API to actually be, again, a separate cluster, right? And then what you're doing is you are removing complexity from your bits. It's kind of like, this is where the Worley maps comes into play, where you have very distinct pieces of units that do one thing really, really well, that understand exactly the inputs and the outputs, and you move the complexity of some of the other areas to other places that introduce other things. So in this case, you have a solution where almost your cluster has, in this case, two inputs, which is basically a place to put a file and an event. And now there's even an argument to say we can even trigger the event programmatically from here. And then you have a place when the file is green, in our case, and in this case, let's track it. So the file goes there. In this case, gets picked up here. The pod goes and gets the file. And then once the pod completes, the pod will put the file and the message there, and then that's what sends over here. So you actually, if you look at this, what you actually have is almost, two inputs and two outputs from a cluster, which you might even be able to reduce to one, right? But if I actually, I think you always need two outputs because you need a message queue, you need a place to go and get it, right? But I really like this workflow because it means that almost like from a design point of view, the cluster becomes this black box, right? And it's this black box that does one thing really, really well. And then you move other things into another cluster that does whatever it is to do really, really well. So in this case, there's lots of things to do to create a secure, scalable, resilience API that has nothing to do with the downstream activities. So because this is exposed to the outside world, there's lots of traffic there, there's issues of caching, security, key management, authorization, authentication. There's also, security, data validation. There's all sorts of things that you want to do that you kind of want to do in this environment, right? You want to do in this environment of the cluster and I would say that you then do that in this particular dedicated cluster, and then and now becomes again your cattle, right? Your disposable entity. So you might have a situation where, from a feature point of view, I see lots of more releases here than I see releases in this environment. So why would I mix that? Why would I, actually not start to segment those? Because you almost let the compute be the division line. And then it becomes a question of how small of a compute can I run these guys? Because we can put a cluster into a very small set of server that then does that activity really, really well. And if you need more, you start bigger and bigger and bigger servers. And you basically put load balancers in the middle of all this, right? So it's a really powerful way and very liberating when you say, I treat my clusters as disposable. I start them, right? And actually Kubernetes, especially the new generation of Kubernetes, servers, like there's MicroKS, there's K3S, where there's lots of really cool, I would say Kubernetes, it's almost runtimes, right? Because they're compatible with the Kubernetes spec. They're very powerful because you can even run these over Raspberry Pi, right? So, of course, I'm not going to do it in production, but just to show you the level of performance that it has. So I really like this idea of having these contained blocks of Kubernetes environments where, you have a very stable, like OS, which is basically the base Kubernetes environment. And we also have this thing with compliant Kubernetes, which is a separate story, but it's kind of a really nice, almost, making, actually, this is the key concept, right? You're making this part serverless. So what you want is an environment where you can then go back to just coding, that bit there, or maybe the API here, in a way that you don't care about the plumbing around it. You just care that it scales. Right? So in this case, I want the developers, when they're making a code change here, not to care about all this. They should be able to ship it. They should be able to run the same environment locally, the same fully featured environment, in their QA, in their development, in low risk, high risk, and medium risk customers, right? But it should all be the same. And it should all be the same with no variations. And then again, if your cluster is self-contained, then you can do that. Right? And also from a security point of view, this is massive because you start to have very clean clusters. You're actually able to really monitor the activities here. You don't have to have a lot of variation, and you can really move into a world where most of this stuff is immutable, never changes. And then, and then you control everything, of course, from CI pipelines, right? By the way, if you have any questions, feel free to put them in the chat, right? So key concepts: one node per cluster, one pod profile, and this addresses one of the problems that we had, which is why the dangers of processing, right? Malware, right, in a reusable pod, right? And I would argue that it's not just malware. Processing things that might leave state, might have memory leaks, might have all sorts of other things that leave on the system. Is because, first of all, from a malware point of view, is that if this guy pops, right? If there's a particular buffer overflow in any of the services running or any technologies that you use inside your pod, then that means that even if you're in a container, the next time you execute the next request, that data is going to be exposed, right? So it becomes quite dangerous because we want an environment where you are pristine every time you execute the malicious code or the malicious data or data that you don't trust. So it's a one pod profile is something that Kubernetes supports, is actually cheap to do, right? Without running millions of them. And it really solves, again, lots of problems, right, in your architecture. So I highly recommend you guys to take a look at that. And one of the challenges we have, so we had two challenges, right? When we did this, right? And basically, and this make a massive difference, right? So the first architecture that we developed, we actually would bind actually this is not correct. It's not network. Is shared data volume. Sorry. So we had two issues that we had here, right? The first issue is how do you give the file to the pod, right? How do you actually give the pod access to the file? And the first design was we actually used the data volume, which actually allows us to say if you're in Azure, bind to the Azure blob storage or S3, put in AWS, put in S3. But he had a problem of having, we had to bind the address, we had to mount the folder in the pod when he did the work. So this was quite problematic because what he meant that we start to fight Kubernetes, because Kubernetes, in a way, tried to protect itself, was detecting that we were doing quite an expensive operation, which is mounting volumes. And mounting volumes, there's a lot of stuff that I think Kubernetes does behind the scenes in order to make sure that the node can access that environment. And it's another good example of something that gets very complex when you have multiple nodes. And then you got this problem where when we needed to start a pod, the pod will take 1, 2, 5, 20, even sometimes 40, 50 seconds to start, right? Because when we wanted to start 10, 20, 30, 40, 50 pods at the same time. So, which is normally not a problem in Kubernetes. You can start 50 pods with a couple of seconds in Kubernetes, but if you try to mount a volume, that value goes exponential. So that was the first major problem that we had, right? The second problem we had was we were creating pods on demand. So that means that we would wait for the request, and the request would then, the adaptation, basically this guy would create the pods. So now you have this compounded problem, which is the more pods needed to be created, the longer they took because of the mounted volume, and we were only creating them when there was traffic, when there was files to be processed. So that was something that we then addressed by this design, and there's something that I feel that it's very important to do when you do this kind of next evolutions, right? Which is it would have been easy to say, well, let's just replace everything in one go, right? Because we now have a new design. But the problem with that is suddenly you don't have a usable system from the beginning, and you are introducing lots of moving parts where you kind of maybe adding more complexity to your system. So what we've done was we said, if you look at the original design, we said, look, we got all these bits working here, and including the same thing here. Let's just replace this pod here, right? Actually, these two. So we want to replace the adaptation pod and the request pod, leaving everything else the same. So the brief was, don't touch the queues, don't touch the input and output. First, address the problem of the scalability. So you can see that the workflow is you get the file, we copy the file to the shared volume, we put the file, the queue, basically in the message in the queue, and this is the same thing as that. So we haven't changed any of it. Then what we've done was we have a whole workflow, which I'll walk in a second, and it ends up by putting the file in the rebuild store and putting the message in the queue. So you can see that from the outside world, this whole new solution still has put the file in the volume, put the message in the queue, which basically means you scale based on the capacity to process the message from the queue, and then put the message back in the queue when you're done and add it to, in this case, the mounted volume. Now we will replace this in the next version, but what this allows us to do is already, for example, support the ICAP server, the cloud, the API server, etc., and others without making changes to them. And then the flow here was what we introduced was Mini.io. And Mini.io was brilliant, right? And Mini.io is basically is a hash-based database. It behaves like S3. And my big question was, what was the performance of it? So I'll walk you through everything, and I'll tell you the performance of this, right? In fact, I'll tell you now. So all of this, I've seen it in runs without the file doing anything. If you don't take this part here as doing anything important, this whole loop can be done in about between 100 and 150 milliseconds, which is pretty cool, right? And basically what happens in there is that you get, and that's actually from here, right? So you get a message in the queue, you basically get the details, you take the file from the rebuild store into the mini IO, and this is why we need to mount. But the good news is we only mount once here, and again then here. So there's only 2 long-lived mounts on it. So this is one of the servers. Then we put a mini IO and we create a signed URL, which we put in the processing queue. So this is really cool, because now you're going to access the file from a URL. So then you put the message in the queue, and then what happens is we have these pods, which are fundamentally the processing pods. And this basically, when they start, they register themselves in the queue. And then when there's a new file, we only deliver it to one. And once that pod takes it, it goes, grabs the file from mini.io, processes the file, put the response to mini.io, and then put the file back into the queue, right? And then this guy's service destroys itself, right? So this service then, right, gets destroyed, and then we start a new one, right? And then this message takes message from the queue, downloads the file from mini.io, put it on the target, in this case, the shared storage, and put a message there. Now, eventually, the idea is that we're actually going to put mini.io and the message queue. So you're going to put this and mini.io as the main interfaces, which basically will make it even more scalable. And then we're going to shave another, 50 to 100, probably milliseconds by getting rid of this part here, right? So that was super effective, right? And again, from a testing point of view, that introduces quite a lot of challenges, right? And then the other thing we do here, which is also super powerful, is that we start 50 or 25 of these at a time. So almost like we do what the Lambda thing, where we run a hard pods. So we have, at any moment in time, there are pods that are already starting, waiting for the requests. And then we have, basically a load balance in front. And then when the request hits, it processes the file, we destroy it, and then, it basically kills itself. And then this service here detects that and starts a new pod, right? And that flow, it happens really, really well, and it's highly scalable. And like I said, round trips of 100 milliseconds, and I still think we can get that lower, right? Introduced by this, which is pretty cool, right? Because he gets to the point where, and then we can process files in the Glassware engine, also, depending on the complexity, but you can have 100 milliseconds, half a second, 1 or 2 seconds, depending on complexity. So I've seen cases where you get full round trips of a file being processed, made safe in about 400 milliseconds, which is really cool. And a server can process 20, 50, 100 of those in parallel. So that becomes, again, super powerful. And that's how we then get to, gigabytes of data and terabytes of data and hundreds of thousands of files being processed, right, in hours, and million files being processed in a big period of time. So the one thing I want to cover too is that we actually did an implementation with serverless, right? So we did a first implementation using serverless, which basically addresses a lot of these, right? So serverless allows you to just, again, execute this pod in a nice way. The problem is most of the serverless implementation that we have today, for me, the biggest problem is they reuse the process. So the biggest thing that you have, which I don't think a lot of people, when they use Lambda functions or Azure functions, understand, right, is that this pod, because fundamentally a serverless function, right, is just this pod that is hot all the time, right? And then gets destroyed, because basically you're providing this workflow. In fact, you don't have the workflow to get the data. It's like HTTP in here and then HTTP out. So basically, in a nutshell, the serverless environments that we have is just a way to start the pods, right, and then make sure that you arrive at the same location for the next request. The problem is that the pods continue to run, or the process continues to run in the, so actually, first, right, it doesn't continue to run because they pause it, they suspend the process after a little bit, but the next request will hit the same process, right? And that for me is a massive problem, because it means that, for example, from a security point of view, it means that if the first request is compromised, then the next request will hit a compromised environment, right? Which is a massive problem. And then you actually have issues like you have memory, reuse, so and leak, right? And temp folders reuse and temp and leak. So in fact, the first time that I hit this problem was that I was thinking that, oh, cool, I don't have to care about cleaning up the temp folder because every time I get a new request. And then I realized that my temp folder from the first Lambda execution was still the same one as the second Lambda execution, right? And I was like, this is not good, right? And I get the value. In fact, you can use it to your advantage, right? There's lots of things you can do, which is great for it, right? But from a security and a resilience and a repeatability point of view, is a massive problem. And there's also memory limitations. We need to process gigabytes of files, files that have, a gigabyte, right? We need to process, we need to run for a period of time. And I know that the latest versions of the AWS have solved all these problems, but there's always some gaps. So we look at support both, but I have to say that, especially the process we use is something that for me is kind of a deal breaker, right? And then this now takes me to so this is basically the whole idea of running 1 pods per file, right? And so the next section I haven't fully evolved, but I'll give it the first pass, and then I'll continue next month with more data, right? So the interesting thing about the workflow I was just describing, and this is the testing ephemeral, Kubernetes applications, is how do you test this, right? When your entire environment, right, can start and be destroyed, and how do you actually, map this out, right? And actually, from a testing point of view, it's a challenge, but it's also a massive opportunity, because what it allows you is to say, look, I'm going to test my whole environment, right? The thing that I really don't like with a lot of test solutions is that you're not actually sometimes testing the end-to-end solution, or you do very limited tests to end-to-end. And the reason why you do that is because you can't set up sometimes easily an end-to-end environment that have all sorts of variations, has basically all sorts of real worldiness, modifications that you need when you're doing certain tests, from deployment straight from a branch, from a pull request, with variations. We have, a level of complexity where, the final solution is made of version 1 from here, 1 version from there, who uses a couple of versions from here. Basically, there's like a tree of probably like 10 or 15 sub-modules or Git repositories that all made up together for the one of the products. And there's other products that we have that have like 30 or 50 components, right? So how do you, synchronize all of those, and how do you test those environments, right? So what I like about this is that you need to consider your test suite that you start at the beginning of your deployment, right? So your test environment, your test scope is basically the entire application, from being created to being destroyed, right? And this is fundamentally the big thing. And the fact that you have ephemeral applications that create and get destroyed, actually make these more possible. And I would actually argue that, any test environment should be pushing to behave like that, to behave in an environment where you can start something, destroy something, start again, play around with things, do runs, compare different runs, because all of that, I don't think there's good solutions for it today, right? Even a lot of the test tools are not designed to support that. And the other thing that I find shocking is there's very few tests for Kubernetes deployments. So there is very few tests for infrastructure, for the planning around this to make all of these components ready. And it's quite interesting that, you look at a Helm chart and you look at Terraform and you look at some, CloudFormation, the stuff, and it's like, well, it's cool because it's declarative. It tells you what you want, right? It says, I want to service, go and figure out how to do that, right? I want to deploy this, etc. That is great, but without testing, right, you end up in the same development mode where you're making random changes, right? You're making things and you're trying it out, and then it works, and then it might not work, and then it's highly inefficient. So the reality is that you want to embrace this situation where you can spin up an environment and destroy an environment, and actually spend a lot of time making sure that is very effective. Because, when you do that all the time, then things that takes an hour become a problem. Things that takes a minute becomes a problem, even sometimes large seconds, because you're running them all the time. So the thing about this, that it also creates, this interesting challenge, because if the pods start and stop, start and start, stop and stop, right, then not only you need to make sure you understand, right, that workflow, your test has to take that into account, right? Your tests have to basically now almost leveraging that capability, right? In fact, the irony of this is that if you look at this architecture, right, I can actually just give you this architecture and say, if this is a test suite, right, then this is one of the best in fact, we have some of this because we have an application that, is a bit similar to this, but there's a lot of traffic. That if this guy, for example, was generating traffic for a website, right, and all you're doing is triggering how many of those particular test scenarios you want from the outside world, you could see that you could scale and you can generate a huge amount of traffic very effectively. So this architecture that I'm describing here is fundamentally also an architecture for your test framework. And this is the thing that I feel a lot of companies don't spend enough time and resources on it, which is your test framework, the coding of your test framework. And if using BDD, the stuff behind the Gherkin commands, etc. But also, your browser automation, your Puppeteer or Selenium, if you guys use that, or others, like you need to spend a huge amount of engineering resources and time and money just on the test framework, just on the deployment of this, right? And I view that this architecture rewards that, but that is not something that happens by default, right? You have to work hard at it. You have to put engineering resources. For example, most QA teams don't have hardcore developers on it. Well, they should. In fact, at least they should have access to it, because or else the QA teams are spending lots of time coding Python or Gherkin or other things, and not actually, basically focusing on the bit that sometimes they're really good at, which is, the understanding of the structure, understanding the tests, understanding the scenarios. On the other hand, if you make your devs do all the QA, right, again, they will automate some stuff, but they don't have sometimes the independence, and they don't understand the side effects of what they're doing. Because what you really want is this world where when you say push now, you want to have this entire pipeline that runs all the test suites all the way to production, or at least a low risk level of production, right? And in this environment of ephemeral Kubernetes pods actually produces some challenges of how you test it, but also gives you a great opportunity from a test framework. Because if you think of these pods as the tests that you want to run, there's a lot of potential, the stuff that you can actually do with this. And then the same thing here, right? Like you want to treat your nodes as ephemeral. They appear, they turn down, they shut down, they go up, then they go down, right? And that is, again, a super powerful way of thinking that, if you have a node, right, and then you add more nodes, or in this case, our nodes are clusters, right? So basically, what we have here is basically this: is we treat our clusters as ephemeral. So we start a cluster, we do a bunch of stuff, and then we destroy it. So for me, what I want to see a lot more is tests during the cluster as it starts. Make sure that everything is set up, make sure everything is configured, make sure that the latest release don't introduce any problems in the clusters. Then run lots of scenarios that represent real world traffic, and then shut it down and make sure that your environment is still the same. Make sure you didn't left anything behind. You didn't left data in a particular blob storage or an S3 bucket or secrets or etc. And you should really be from zero, right, to everything running, to a bunch of scenarios that you do, to then actually capturing that in another system, so you persist all of that, and then you destroy everything. And that's kind of, the final point here, is that you want to make sure that your entire pipeline is also tested, including, of course, the pipeline, but everything you got in there has to have this level of tests. And these clusters actually allow you not to mock things, which is something I always have a big problem with, where when you're mocking stuff, you're creating a version of reality. So it's way much better to have the actual real thing that you can then run and have test suites that generate all that traffic. And then when you're working on one of the components, you just almost work serverless in that mode, the environment. Like you just deploy stuff, and then you should be able to see, and we use Elastic quite a lot in Kibana, quite a lot, so, and Grafana, and you should be able to see and monitoring what is actually going on in there. And that's it. So I want to add a lot more for the next couple of months. I'll redo this presentation again, and I'll show a lot more evidence and a lot more examples on how we're testing, what our pipelines look like. We're now trying a bunch of other different tools that I think are going to be very relevant on this. So I'll be able to show a lot more data, and I'll show you also a lot of our test runs, including the runs that initially have lots of failures, that didn't scale very well, and the latest set of runs where we're actually getting a huge amount of horsepower and huge amount of capability out of the servers with our, again, the hot pods and all of that. So you guys have any questions on the chat or on audio? If not, I this is my presentation.
Nothing from my end. Thanks.
All right, man.
Was a lot of content, I would say. I mean, a lot of information. So, but yeah, very useful.
Yeah. Well, so
Thanks
that's
a lot.
why we recorded, right? So you can then go back, right?
Yes.
And then, again, put comments on the Open Security Summit stuff, and let me know what areas, right? I can zoom in on any of these, right? I can spend a whole day talking about this stuff, right? So
sure.
Cool.
I will.
All right, let me stop recording. So again, thanks everybody. And